Hello everyone, my name is Omer and today with Rafal we will talk about the novel programming models for HPC. First, I will tell the motivation of the project. HPC architecture is evolving and HPC systems are getting more heterogeneous over time. Increasing use of GPUs is the best example of it. As HPC architecture is changing, new programming models are also being developed to take advantage of the heterogeneous architecture. Aim of this project is to analyze these models and make a comparison between them. Here are the novel models we tested in the project. Their names are Cocos, XcalableMP, Trust, Charm++, and Adaptive MPI. Now I will talk briefly about them. The first one is Cocos. Written in C++, Cocos aims for producing performance portable applications. It supports CUDA, HPX, OpenMP, and pthreads as backend programming models. Next is XcalableMP, XMP for short, a C and Fortran extension. It is directive-based and also provides an MPI interface. Trust is written in C++ and it resembles the standard template library. It supports CUDA and OpenMP backend. Charm++ doesn't have its own logo like the previous models, but it has its unique features like dynamic load balancing. It is based on C++ and it is an object-oriented system. The last one is Adaptive MPI. It is related to Charm++ because it is built on Charm++. In addition, it is an implementation of MPI. We tested the models using two approaches. First, we tested the models with BLAS routines, which stands for Basic Linear Algebra Subprograms. Then we tested the models with a real case application related to biomedical engineering. To give general information about BLAS routines, they provide basic vector and matrix operations. These are the routines we used for our tests. All of them use double precision variables. First routine performs dot product, second routine performs matrix vector multiplication, third routine performs matrix multiplication, and the last routine solves a triangular matrix equation. Here is an example comparison for Cocos and Trust. Cocos and Trust seem close to each other in each plot, however Trust seems a little better overall.
We also tested some BLAS routines with XcalableMP and Charm++. We used the following routines, which are a dot product of two vectors, multiplication of two matrices, matrix vector multiplication, and solving triangular matrix with multiple right-hand sides. And we've tried them for some different matrix vector sizes and for a different number of cores. And here are some results obtained from the calculations. First, from XcalableMP. We can see that the dot product calculation of two vectors done sequentially is much faster than done parallel. If you think of that, it seems as expected because dot product is a pretty simple operation of just going through vectors, but the overhead of copying the data back and forth, which is required by this framework, is bigger than just going through the data sequentially. For matrix multiplication situation is much better because copying the data is done in linear time and the operation of multiplication is done in n cubed. So there is a huge difference when multiplication is done in parallel and copying time doesn't matter that much. For matrix vector multiplication situation is similar to dot product calculation, and for solving triangular matrix is similar to matrix multiplication. One can see that when the number of cores exceeds some value, the time gain does not increase anymore because of context switching and the synchronization that takes place. For Charm++, we used the same routines as previously, but with this framework there were some issues. Up to a certain number of cores, the execution was similar to the one with XMP, but when the number of cores exceeded a certain threshold, the time suddenly soared and it seemed like the program was stuck. What is interesting that it not always takes place. Sometimes it works normally and sometimes it is not. But there is a bug reported on the framework's GitHub page, so it may be fixed in the future. Finally, we decided to implement two biomedical applications, DNA sequences comprising the creation of a Dotplot from them, and DNA sequences global alignment. As previously, they were tested for some different DNA sequence length and for different number of cores. The first application creates a matrix dot plot from 2 sequences of DNA. For every nucleotide from S1, you have to check every nucleotide from S2, and if they are the same, put dot in matrix in the related place. And if nucleotides are different, leave the place empty. So the program is just element-wise checking of the two vectors, but it allows us to see, for example, if there are some similarities between two organisms. And we can see from the generated picture that there are some insertions, deletions, duplications, and so on. The second program takes two DNA sequences and aligns them together, connecting related nucleotides and making gaps in sequences if there may be some insertions and deletions. The algorithm is much more complicated, so it will be described in the final report. Just by looking at the timings for XMP, one can see the similarity to the BLAS routines. When using XMP for parallel DNA alignment, we can get a huge drop in time spent for calculations. For Charm++, the results are also bad as previously. Some weird framework behavior is just messing the results, but for up to 4 cores there is some time gain, but not that much as it was for XMP. We also tested these two biomedical applications with AMPI, which is built on top of Charm++. Although the documentation is quite poor, which makes programs not so easy to write, XcalableMP seems to be the most stable framework and have quite predictable behavior. Additional thing to consider is the amount of memory used by this framework due to its lack of co-array runtime allocation. Charm++ and AMPI are really nice to write programs in because they are very intuitive and pretty well documented, but not all the documented features really work. These frameworks use network to pass messages and share data, and it may be really tricky sometimes and cause a lot of problems. Not all programs are good for parallelization, and many things have to be considered, especially if the size of the problems is not so large.